Now we've learned a little bit more about R squared. We're going to look at how we can use it to make inferences. So one of the reasons R squared is such a useful effect size is because we can really make inferences using it directly. If we have several predictors and we want to see how much they contribute to an R squared, we can simply fit a reduced model and check the difference in the R squared from the full and reduced model. So today, it turns out, is actually my favorite day of the year. So this is for the day we're having the lab, which is April 5th. So it was originally supposed to be last week, but due to some unfortunate COVID issues on the opposing team, Mets opening day, the New York Mets opening day was pushed back to today. I'm a huge baseball fan, and so I'm very excited. And I will be spending my evening parked on the couch watching a baseball game, which is the first time this year, which I'm very excited about. So for today's example, we're going to be looking at some data about baseball. We're going to be looking at how many games, if we can predict how many games a team will win based on the quality of their offense, pitching, and defense. And so the baseball 2019 data set is a real data set from the 2019 Major League Baseball season. That's 30 observations, so there are 30 teams in baseball, so each row is a team. So one of the first variable is the name of the team, and this is just for reference. It's an abbreviation for the team name. Second is wins, how many games they won. Then attendance, which we'll use later. Average attendance, and remember this is 2019, so there were full stadiums in 2019. So then there's the total number of runs the team scored over the course of the year. This is a measure of their offense. ERA, which is earned run average, which is a measure of the quality of the pitching. And then defense. So this is a measure of the skill of the team's defense, with 0 being average. So in baseball, pitching and defense are kind of similar. They overlap quite a bit. The goal in both cases is to prevent the other team from scoring. So the defense is essentially how the players in the field catch the ball. The pitching is how well the pitcher throws the ball. And traditionally, it's assumed that pitching carries greater responsibility for preventing the other team from scoring than defense does in baseball. But let's figure this out. So if we wanted to estimate how much about total wins, defense adds over offense and ERA, so pitching and runs, or pitching and offense, ERA and runs. We fit 2 models. So the first model uses the 3 predictors plus an intercept to predict wins, and then the second one deletes defense and just has runs and ERA. So first, let's define new terms. So the residual variance of the model is simply the variance of the epsilons of the errors. So it's this the sums of squared errors in the model. So we can denote this sigma squared epsilon. So we obtain this where n is the sample size and p is the number of predictors by multiplying it's the mean square, not the sum of squares, by multiplying the residuals by the vector of residuals by itself. That's the sums of squares, residual, and then we divide it by n minus p minus 1. So what's going to be bigger, the variance of the residuals in the full model, or the variance of the residuals in the reduced model? So the variance of the errors in the reduced model is going to be larger. The reason for this is that in the full model, we have everything that we're able to explain about the variance of the residuals is included, but the full model has 1 extra predictor. So all of the information in the reduced model is contained in the full model, and the worst case scenario is this extra predictor is just going to add more noise, which means that it will not necessarily decrease the residual variance in the reduced models, but it can't increase it. It can only really decrease it, because the worst case scenario is it's just adding random noise. So what about R squared? What's going to be bigger, R squared full or R squared reduced? So for the same reason, R squared reduced is going to be bigger, because R squared is R squared is the reverse of the residual variance. So based on the same logic, even if defense is just adding noise, which is the worst case scenario, then r squared full equals r squared reduced. Otherwise, r squared full is going to be bigger. So in this case, since the reduced model is nested within the full model, which it should be, we can estimate the contribution of defense above and beyond runs in ERA as by subtracting the r squared of the reduced model from the r squared of the full model. And that gives us, we'll call here r squared delta, or r squared difference. So let's see how we can apply this. So here I'm going to load up my data, and I'm going to fit my full and reduced model. I'll check the r squared of the full model, and I'll check the r squared of the reduced model, and then I'll get the difference. And we see the difference is really small here. So this sort of implies, since the r squared change is so small, that defense does not explain a lot about total wins above and beyond hitting and pitching. So runs in ERA explain 96% of the variance in total wins, and defense explained less than 1% more above and beyond ERA and runs. So it doesn't seem like it added too much, but we can test that. So if we define the sums of squares regression, like I explained before, as the squared residuals, the vector of residuals times itself, we can then test the null hypothesis that the beta associated with defense is 0, or equivalently that the r squared change for this predictor is 0. So here we have two equivalent formulas which can both give us an F statistic, or are distributed on an F distribution. So we can take the sums of squared from the reduced model minus the full model divided by P minus Q, where Q is the number of predictors in the reduced model and P is the full model, and then divide that by the residual variance of the full model. Or alternatively, we could take the delta r squared divided by P minus Q divided by 1 minus r squared from the full model divided by n minus P minus 1. So these are equivalent, and they'll both give you an F statistic on a distribution with P minus Q and n minus P minus 1 degrees of freedom. So instead of going through all the matrix stuff to get the residuals and all that, we can just use the predict function just to see the way this works first. So we could use the predict function to get the estimated values by the model, the predicted values, so the y hats. And then we can get the residuals as the actual y's minus the y hat. So here I use predict to get y hat, and then I get the residuals as the actual wins minus y hat. And so we can see here's just the first 6 residuals. An even easier way is we can just use the resid function. The residuals are actually in the LM object here, and this is just a way to pull them out. And so you see this is just a simpler way to get the residuals. I just wanted to show you the first way just to sort of solidify concretely what the residuals were. So we can always just use the resid function. So now I'm going to set my n, p, and q. I'm going to get my sums of squares and my sigma squared epsilon, and plug in to get my f. So my n is the number of observations, so it's going to be 30. P is 3, since I have 3 predictors in the full model. Q is p minus 1, since I deleted 1 predictor in the reduced model. So the sums of squares for the full model is the squared residuals. Sigma squared epsilon is sums of SS full divided by n minus p minus 1. Sums of squares reduced is the sums of squared residuals from the reduced model. And then my f, I can plug into either the sums of squared version or the r squared version and get the same f statistic here. So this is just plugging into the formulas that we saw a few slides back. And so we see the f is very small, it's 0.14. And so I can then plug that in. You can ignore that this says r squared. That's just because I use the r squared to compute it here. So I can plug into the PF function to get my p-value. So of course we could get this result all much more easily, and in practice, this is the way you would do it. So you would enter both models into the little a Anova function, and this would compare 2 nested models. So we would say the effect of defense on wins above and beyond runs and ERA was not significant. F of 126 equals 0.14, P equals 0.71. So we can also generalize this technique to models that have more than one predictor deleted. So let's say we just wanted to see the effect of, we wanted to see the opposite. We wanted to see how much wins and, or I'm sorry, how much runs and ERA add above and beyond defense. So we can fit a reduced model based on just defense as the only predictor. So we see here it has an R squared of 0.15, and we can then get the difference between that and the original full model, which has the additional 2 predictors. So this is the effect of hitting and or runs and ERA above defense. And so notice, interestingly, on its own, the R squared for defense isn't nearly as small as the R squared delta we got for defense before. So that's because the predictors are correlated. So most of the variability defense explains can also be explained by runs and ERA, and there's some variability that runs and ERA explain that can alternatively be explained by defense. They share some of the explanatory power. And so here we can get our Anova table again the same way, and we get our test statistics. So same thing we saw before, just with a different, with 2 predictors deleted. So in the first example, when we had just one predictor removed, our degrees of freedom for our test statistic were F 126. And so when the first degrees of freedom in an F are 1, we can convert it directly to a T with the second degrees of freedom. So in this case, T of 26. Anyone remember how we do that? So it's just F is the square root of F is T. So an F with the first degrees of freedom, the numerator degrees of freedom being 1, just converts to is just T squared. So just remember that when using the PT function, we have to multiply by 2 for the 2-tailed test. But here you see I just plug in the square root of my F value from my first example into the T statistic probability function, and I get the exact same result. So I get the same p-value that I got before. And so this is the reason I mentioned this is because this is what you see in the summary output for an LM object where you have T statistics for each predictor. So this is really just the square root of the F test essentially with degrees of freedom, the first degrees of freedom being 1. So you can just, it's more straightforward to write this as a T statistic, which is how you'll sort of conventionally see these regression tables with a T value, not an F. So most of this should really have been sort of a review, but now we're going to talk about something that's probably pretty new. And so what we get in these regression examples are 1 at a time T statistics, which test the null hypothesis for each variable above and beyond the others. We can also get the individual delta R squares for each predictor above and beyond all the others at once. This still doesn't give us a great picture of how to compare the importance of each predictor within the model to one another. It really just explains how much they explain independently of the other variables. So one way to do this was actually developed in part by David. It's called dominance analysis. It's a really nice technique. So this is a way of assessing the importance of each predictor in a regression model as a fraction of the total R squared. And so this is a procedure that compares all possible nested subsets of a regression model. So the way we're going to do this is we're going to begin by fitting all possible models that do not contain our target predictor. So these can each have up to p-1 because we have one focal predictor. We want to figure out how important it is. So we're first going to start by fitting all models that don't have that predictor. So in our example, p equals 3. That means we can have regression models that have either 0, 1, or 2 predictors that we're going to start with. These are considered the levels of the model. And then for each of these models, we can estimate the R square change we would get by adding the predictor of interest. So next we are going to average the delta R squared for our target predictor at each of the k levels separately. So we're going to go level by level and average the delta R squared across each level. And so where M is the number of models at level K, we're going to go through each level K, and we're just going to average across all the delta R squares. Then we can get the contribution average by averaging all of the contributions at each level. So now we have, in this case, we're going to have 3 different contributions by level, because we're going to have one for 0, 1, and 2. So this is going to go from 0 to p minus 1. And we're going to take the average of all those, and that's going to give us our contribution average, which is the value we're after. And the sum of all these contribution averages will total the total R squared of the model. So this is a way of decomposing the R squared, predictor by predictor. So in this example, I'm going to look at the contribution of ERA to our model. And so when we have k equals 0, we have just one model. This would be a model with no predictors, which is intercept only. And the delta R squared we would get by adding ERA is just the R squared for the model with ERA as the only predictor. So at level 0, the delta R squared is just the R squared of ERA predicting wins on its own. At k equals 1, I have 2 models. I have one with only runs and one with only defense predicting wins. And to get my delta R squares for these models, I create then a new model in each case that adds ERA as well. And then I get the delta R squared for both of those. And then at k equals 2, I have just one model again, a model with runs and defense predicting wins. And again, to get the delta R squared, I create a new model that adds an ERA, which is essentially our full model. And then I get the delta R squared for ERA from our full model compared to just hitting a defense. So here's how we can, this is just showing the long way to do this. I'll show a much easier way. This helps us understand exactly what dominance analysis is doing. So at k equals 0, my delta is just the R squared for ERA predicting wins. So then for, if I want to get k equals 1 and k equals 2, I need to fit a bunch of models. So first I'm going to get the R squared for runs alone and the R squared for defense alone. And then I'm also going to get the R squared for ERA and runs and ERA and defense. So that this is going to let me get my deltas at k equals 2. For k equals 1, I'm sorry. So the k equals 1s are going to be the delta for runs and ERA minus just runs, and then defense and ERA minus just defense. And then for level 3, I'm going to first start with a model with just runs and defense, and then I'm going to get the R squared of the full model here again. And then I'm going to take the R squared difference from the full model and the k equals 2 model. So I have all R squared deltas I need now. So now I need to get my contributions by level. For k equals 2 and k equals 0, we only have one model, and so we don't need to do any extra averaging. That is our contribution by level, but for k equals 1, we have 2 models. So for k equals 0, this is just the contribution average is just the delta at k equals, for that one k equals 0 model. At k equals 1, we need to average the contribution across the 2 models at this level. And then again, at k equals 2, we only have one model. So these are the contributions by level. And then to get my contribution average, I average all the contributions by level, and this is my contribution average. So this is the contribution of my predictor to the total R squared, the contribution of ERA to the total R squared. I can also compare it to the full model to check what proportion of the R squared, proportion of the total R squared the predictor explains. So in this case, I just divide contribution average by the total R squared. And so the interpretation here is when compared to runs and defense, ERA contributed 0.44 to the total R squared of 0.96 of the 3 predictors on total wins, and that's 46% of the total R squared. And that was many steps, which was mostly done to show you the way this procedure worked. But of course, there is an R package. It's called dominance analysis. So it includes a dominance analysis function, which gives us the contribution average. So load up dominance analysis and then run my dominance analysis. So here we see our results for each predictor. And this notice that it matches our result for ERA here. Just rounds it off, but 0.438. And we can also use this to demonstrate that if we sum up each of the contribution averages, we recapture our original R squared of our full model. So this is a decomposition of the R squared. So the only sort of issue that you can run into with dominance analysis is that when there are lots and lots of predictors, like when you start getting like 11, 12, it can start to get slow. And it gets really, really slow when you have more than 12, 13, 14, 15. And it can take a long time to run. The reason is that it has to fit exponentially increasing subsets of all possible models to get the contribution breakdowns. But it is a really great way of assessing predictor importance in multiple regression models that aren't like machine learning level big data models. In which case then it can get pretty slow.